Welcome everyone to the latest HACC Tech Talk in our summer 2024 series. My name is Naveen Purushottam, and I'm from the AMD University program, and I'm very pleased to be able to welcome our two speakers for today. But before I do that, I'd like to briefly introduce our HACC program and this series of talks for anyone new to the HACC community. The HACC Tech Talks are intended to highlight some of the applications and research related to Heterogeneous Accelerated Compute Clusters program. The program is a special initiative from AMD to support novel research in heterogeneous accelerated computing. HACC centers have been set up at partner universities around the world. Our newest HACC is in IISc, the Indian Institute of Science at Bangalore, and each HACC consists of compute nodes enabled with AMD EPICs, Alveo, Instinct, and Versal computing hardware. Participants in the HACC program can access these nodes remotely for their own research. If you are a researcher working in high-end compute and related fields, we'd invite you to join the program. You can find the details on the webpage shown on the screen here. So our first speaker today is Dr. Chiranjib Bhattacharyya from the Indian Institute of Science, Bangalore. He's a Tata Chem professor in the Department of Computer Science and Automation, and his research interests are in the foundations of machine learning, optimization, and their applications to industrial problems. He will present on the topic pruning in the data-free regime, a distributional approach to structured pruning.
So welcome everyone. Naveen forgot to say, he said 8:30, but 8:30 where? It's 9 p.m. here. And so it's good evening for us, for Indian colleagues, and good morning to people who are joining from Pacific, and good afternoon from other geographies. It's extremely pleased to give this talk here, and I'm extremely doubly pleased to give the first tech talk from AMD HACC IISc Center. Naveen already announced the title of the talk, and so if some of the things looks a little bit foreign to you, I hope I'll explain this. But since it's the first HACC talk from the newest HACC Center of AMD, so here is our team here at IISc. So there are 5 projects. So Professor Govindarajan and myself are leading one of them, hardware hour inference, and I will talk a little bit on some progress we have made on this problem. And there are 4 other projects going on, and Professor Sumit Mandal, who after me will speak on progress on his project. So here is our team. Like as you can see, big team, and we're extremely pleased to have AMD colleagues here also working with us, and some of them have graduated. So we are going to talk about some work which we did with Tanay, Chaitanya, and myself. So this came out as papers in ICLR, a leading conference in machine learning and AI. So this is on the theme which we are going to speak about now. So broad theme is that how do I do pruning in the data-free regime, right? So in other words, the main theme, we got excited by this problem when we were thinking about how to do efficient inference. So just a motivation, and this paper really shook me to the core when I saw this. So you can see this is a very famous paper where they tried to, measure the energy consumption of some very popular deep learning models. So there are much bigger models now, but so this would be the energy consumption per iteration of training. Now, what is very shocking is the carbon footprint of the training cost of these powerful models. Now, the first thing, if you see the BERT model, right, it says the CO2 equivalent is something like 1438. Now, for example, the transformer, 200 million parameters, it has some number. Now, get a full sense of this number, the authors contextualize it using this interesting description. As you can see, air travel from New York to San Francisco is something like 1984, right? Which is roughly one iteration of the BERT training algorithm with 1438, right? So the average lifetime of a car, so training a 200 million parameter transformers is equal to 5 times the carbon equivalent, the CO2 equivalent of a lifetime of a car. So it's quite shocking in more ways than one. So those of you who are aware of this, you can read more about this. Those of you who are aware, you already know, and those of you who want more reference about this, you can read this paper where these numbers are taken. So clearly, this is way off for us. And now when you probe even further, this NVIDIA chief, right? He has a very famous quote. I mean, it's well known, but just to make the point, so he says most of this cost, apart from training, there's another cost of AI that is 80 to 90% of the cost of machine learning at scale is basically AI inference. So inference is, what is inference? Inference is think like this, that every time I query ChatGPT with any question, ChatGPT comes back with an answer. So that's the inference problem, right? So inference cost, given today's day and age, as it's rising, it would soon make AI unsustainable unless we can find other ways. So this is the perspective we started from. Sorry, what happened? Where it went back? Yeah. So then we started looking at deep networks. So the usual strategy, or the strategy is, you start pruning things. So what is pruning? So pruning can be thought about like this, that, the model has many parameters. So now if we throw away those parameters, the model becomes smaller. Hence, I should be able to, it should show up as a lower inference time, right? Now, just to be clear, why lower inference time? Because in the last slides, we saw energy. So basically inference, so power into time is basically energy spent, right? So if I get the lower inference time, hopefully it will translate into lower energy. All right. So now, structure. So basically, one thing is that you can take weights and make them to zero. For example, things in the slides in the right, the picture on the right, things which are white can be understood as being gotten rid of, right? Now, most deep networks, especially, let's say the standard feed-forward networks, has a little bit more structure to it. For example, they're organized in the form of filters and other things, right? Now, if I just take things and randomly zero out, it can go over multiple filters. So this is one end of the story. Another end of the story, some people thought that, okay, it's better that, you can structurally remove things instead of putting, if you're carefully picking up weights here and there, you can do one more thing. You can just pick up the structure which you have, and throw it out. For example, so if these are filters, then you throw away these filters, right? Now, between the two, for example, if you can do unstructured pruning, unstructured pruning means I just put weights to zero, right? And structured pruning means, I throw away a group of things. Now, the challenge seems to be that, see, our goal is not to, our end goal is not to cut down the number of parameters. That is just a means to an end. Our end is to get inference time low. Now to get inference time low, it is very, at least in the modern day understanding, is that just putting weights to zero does not, we do not have the engineering to show that it will lead to a lower inference time. Whereas if we start pruning out entire structures, maybe I'll get better inference time, with no additional special hardwares or no fancy codes written. So that's why the idea of structured pruning is, has gained currency in the field, and so that's where we are now. So now the thing is, where we got started off from was this following problem. When we talked to several startup companies here in Bangalore, I mean, this is just chance discussion. So they were saying that what they usually do is they download models from the internet and then they train it. Now, and often they find that the models are too big to be deployed in the scenario they have, and hence requirement for pruning. But their challenge is they do not have access to the original trained data set. They do not have any idea about, what is the algorithm used, what's the loss function used, and things like that, right? So while when you looked at the literature, we found actually most algorithms often assume assume three things that are available to them. One is the model, second is the training data set, and third is the procedure, or not procedure, maybe an algorithm or the loss function, which they've used to train the network. Now, clearly, the availability of the model, availability of the training set and the loss function and stuff like that, which they used to train, are clearly not available in most cases. And as you can see, more and more sophisticated models are come out in open source. These things are these kind of assumptions would be wrong. So then this sets up. So the question then we are pondering about was, if training data is unavailable, how do I do pruning? And so there are many, and we raised a few questions, and there are other more pressing questions like privacy and security and things like that. So we found that this is a very nice ground for research. Not much has been done. While pruning has a huge literature these days, but if we say training data is not available, that's a nice research space, and which has immediate applications and things like that. So that's where we started from, and henceforth the definition for data-free regime would be that not that we don't require data, we of course require data, but we said that we don't have access to the training data. And now, can we do pruning? And now, as we can understand, we're interested in doing structured pruning, right? So that's the setup of this problem. Now, so this is where we are struggling with. Now, if you want to write down a desiderata of such a structured pruning algorithm in the data-free setting, right? So now, here are things, when we reason it out, here are some 4 or 5 things that comes to mind. For example, we are given a model which is essentially well-trained, right? Now, I don't have training data and all that, so I can't easily do experiments and mimic it, right? So then I need to have a good characterization of a well-trained models, right? Now, this other thing about pruning is often what you do is your recipe is, you check either your weights or your structures, in this case filters, you try to prioritize them, which one to keep and which one to prune through a score. And the score is often derived through the loss functions and things like that. And then what you do is retraining. So our characterization of a well-trained model should help, it will be such a way that will help me prioritize which filters to prune and things like that. Now, retraining, that is, now once you prune things, to get back your accuracy, often what you do is you take the training set and retrain. Now here we don't have access to training set, right? So now, and ideally, even if access to training set, training such large volumes of data essentially remains a challenge in itself, right? So can we do away with retraining? That should be one of the other desiderata. And now there is also this talk that, depending on, especially for example, a company like AMD, right? You have this nice hardware platforms. Intel has one, NVIDIA would have one, and all that. So can you exploit the some architectural properties to show even better speed up and things like that? But end goal is that we should have better inference time. Now, there's a lot to be done in this space, and we're going to present some results to some extent in various papers, which touch on some of these points. So first of all, so no access to training set, right? So how do I even start thinking about this problem, right? So now, so first thing we thought about is this following thing, So imagine there are 2 filters, right? So sorry, imagine there's one filter, and now you feed to the same filter, you feed the image of cats, right? And let us say the filter output is a number for now activation of some things, right? And you see that the activations varies according to that blue curve, right? Now, if we say that the if I freeze dogs, you say like we get another curve like that, right? So let's call this as filter output, right? Now, if you said that, okay, I want you training set, but of course you have told me that for what kind of things you want. You said, no, I want my network to be good, or should have high accuracy when I see cats and dogs, right? So now, if cats and dogs is what we want, all we need may not be the exact training set, because machine learning comes with the perspective that it should work on unseen data so long as it's generated from the same distribution. So that means now I can go and shoot some images of cats and dogs. And hopefully, if I get these responses correct, I should be done. And that's the whole idea, that even if without training set access, how can I solve this problem, right? Now, so this sets up our goal. Now, since you have now said that, okay, what I should prioritize. So since you have the filter response, by filter response, I mean the distribution of the filter outputs, right? How this changes, right? Now, suppose there are two filters. One is pink colored and one is green colored, right? Now, I present the images of cats and dogs to both the filters. Now, if you look at the output of the green colored filter, right? Suppose the output was like this. So the brown color is basically the response to dogs images, and the blue color response is the response to the cats images, right? Now, clearly, the pink colored one responds differently when they sees dogs and cats. Now, if my end goal is to recognize dogs and cats, this is the filter, I should preserve, right? With a green colored cat filter, often doesn't show that, right? It is reacting the same way as it for both dogs and cats, right? So this idea is inspired by what is known as discriminative learning. It's a very classical learning strategy, and that's where we thought we can develop this idea that we look at the filter response, that is the probability distribution of the responses of the filters, and then try and see that if you can identify discriminative filters, and then you can do pruning with this. So that's basically the idea. Now, the key question we asked earlier was that we need to characterize a well-trained model, right? So now our characterization is as follows, and we came through some experiments that see most well-trained networks have this, that there are significant fraction of discriminative filters, and those are the things which gives you high accuracy. So often, the modern deep networks actually solve two problems, which was previously solved differently. One was the representation, another was the accuracy, for that matter. So previously, before the arrangement of deep networks, often this was done separately, but the deep network nicely combines these two things. And that's why you see that you throw any data at it, you never put more number of neurons, it gives you high accuracy, right? So the non-discriminative filters, even the reason why they should be present is that even they may not directly add value to discriminative part of it, but they still have some role to play in giving efficient representations, which can be exploited by the discriminative filters. So basically, but the key implication is that suppose if you have a large enough network, right? So then the key thing to note is the discriminative filters are the key to generalization. That means, so it opens up opportunity for us for pruning, that if we can preserve the discriminative filters, we should be good to go. All right, and because they are the ones who are key to the generalization error, right? And so of course, can this be verified? Yes, we can verify this, and we did, and more is found in the paper which I flashed before. But then the comes to that, okay, fine. How do we even measure discriminative ability? Now, here is a joke, like a very famous cartoon, Calvin Hobbes, those of you know. So Calvin says, okay, great things are happening, but we should look at more television, the TV shows, right? So TV has a different term for us. It is known as total variation distance. So the idea is that we can identify discriminative filters by using total variation distance, which is basically a distance between of probability distributions. So now, as you said, the filter outputs essentially, the way we want to look at it is the distribution of the filter outputs when I show them various images of cats or dogs, right? Now, if you can look at the filters and try to come up with, how far these distributions are in the total variation sense, right? And that gives us an idea about characterizing the goodness of the filter across various classes. So mean TVS is one score, which is basically the total minimum of total variation distance across all pairs of classes, right? So let's say this is a mesh. I'm running out of time. So what I'll do is I will just quickly flash these complicated formulas. This is just to say that so we can get closed form expressions under some assumptions. And this formula and these things can be easily measured, and this often depends on the moments of the distributions, right? Now, so that is, you take a forward pass with network, you can easily compute these numbers, and we can, using this theory, we can now compute a score per filter, which is basically computing that how discriminative it is. Now, once we have that, then we can use it further. And one of the first things we did is that we said that, okay, the key hypothesis is, and that's what the things are, that there's a mix of discriminative versus and non-discriminative filters. Now, and of course, that means our things will work well where there are, where there is like a low number or high number of non-discriminative filters, and low number of discriminative filters, etc. So the idea is that there is also this understanding in the field that some layers are easy to prune and some are not. For example, in the initial layers, the number of discriminative filters are very low. That is, initial layers are mainly for feature representation. But after that, you see that the more number of discriminative filters appear. So relative score is a tau is a number between 0 and 1, which is like a fraction of discriminative and non-discriminative filters determined by the previous formula. And you can see as we go higher up the layers, right, we see more and more discriminative filters. And therein lies the opportunity of pruning things, right? So maybe I'll skip this. So now here is a very interesting result. Now remember, we haven't seen any data. So what we did was we took cats and dogs images, right, and look at the filter outputs, right? Now, if you can see so now here is on the x-axis is the number of percentage of the parameters which we have pruned, right? And on the y-axis is the accuracy drop, that how much did the accuracy suffer. Now, this is one example of EGNet, which is an image problem, and CIFAR10 is a 10 class problem. And you can see roughly if this even is 20%, percent. So that means even if I remove 20% of the data, the accuracy roughly remains the same. So that's amazing, because this can identify this filters which are discriminative, right? And of course, after that, it slightly degrades, but degrades much worse than other methods. And of course, after that, you may have to retrain things and things like that, right? So now, so TVS prune is the algorithm we talked about. The chip is a very powerful baseline, but it requires access to the original training data. Now, so this shows some of the validity of our results. And of course, you can see more results are there in the paper. Now, since I'm almost, I think, around off time. So here are quick two comments about the other problems we mentioned. One is basically that does it lead to inference time reduction? So while that is a good approach, that it doesn't require training time, it doesn't require training data, but still there is a gap. But to do, let's say, a problem which even gives more aggressively, reduces inference time. So one of the things one of the students identified, Tanay identified that there is this coupled connections in these complicated layers, right? And these are the ones which most pruning algorithms don't touch, but they consume 66% inference time. And so therein we had a very nice algorithm which shows that you could have CPU speedups way more than existing algorithms. So we are pressing on this front as well, and So now we also mentioned, now this is future work, we also mentioned that we do not require retraining. So now we have new results now. So, so now where we say that most networks have a batch norm. Now, if you can look at the batch norm statistics, and using high quality statistics, I would say we have come with a fix for that. So we call BN fix. Now, basically what you do is we have this network, we did pruning and all that, then you just change the batch norm statistic a bit. And it is probably as good as retraining. Of course, not really as effective as retraining, but it's pretty close to retraining. So we are writing it up and hope to present somewhere this result soon. And then we are now venturing into what is known as model editing. I'll show one slide on this. Model editing can be seen as a broader class of problems which includes pruning. So the model editing problem is as follows. One of the problems is class unlearning. That's, can you forget class 0? Can you forget class 1? Now these things are coming because there's this thing of a right to be forgotten. So here is one thing, that the discriminative filters also gives us this interesting proposition, that you just have to remove, or you just have to target that which filters are most discriminative for that particular class. So this blue class is, so basically if the blue bar, so let's look at the first bar. So class 0, right? So suppose we have been mandated with the problem that you have a well-trained model, you need to forget class 0. Now see, the initial accuracy, the blue bar is the initial accuracy. And the complementary class is that other red colored bar, right? Now, just by identifying our results, right? Identifying the discriminative filters, we come with a very simple algorithm, and then you see our yellow bar is the new accuracy. Now that means it is doing very poorly on class 0, which was doing very well, but in the remaining class, it doesn't suffer. So the green and the red should roughly be the same, right? So blue and yellow should be very different, but the red and the green should be roughly the same. So you see, some more exciting things have opened up. My colleague, Professor Govindrajan, he's also pressing very hard on platform-aware pruning, which I said. So we have found staircase patterns on platforms on how CNNs have been engineered. And this opens up new opportunities for pruning. For example, and it shows not huge, but significant speed up in inference time. So that was a very quick tour de force of what we are doing. In a nutshell, I want to thank AMD for giving us this opportunity to work on this very exciting problem. And I thank the audience for listening to me. Happy to take any questions.